Every time a Raptor engine fires up, it begins a precise and precarious performance on the very edge of catastrophic failure. Every single component that makes this thing function is so deeply connected to every other component, operating under such extreme conditions that if anything drifts even slightly out of alignment, everything comes apart violently. And if we can truly understand how this engine works, we can better appreciate why SpaceX chose to build something this inherently dangerous. Because when you look at the full picture, the Raptor turns out to be the only viable answer to what seemed like an unsolvable problem. And it all starts with a much smaller company, building a much smaller engine, chasing a much more modest goal. 20 years ago, SpaceX just needed a rocket capable of reaching orbit before the money ran dry. They called that rocket the Falcon, a reference to a spacecraft from Star Wars, but also a bird of prey. The engine powering it would be called Merlin, the name of a legendary wizard, but also a bird. A small member of the Falcon family as it happens. Behind the clever naming though, the early days of SpaceX were frankly just organized chaos. For a private tech startup out of California to enter the field of orbital rocket launches in the early 2000s was not simply unprecedented, it bordered on madness. Nobody believed they would pull it off, and as a result, nobody was putting money into it. Elon Musk was bankrolling the entire operation using his own fortune from the PayPal sale, which was substantial, but SpaceX was burning through cash at roughly the same rate they were burning through rocket propellant. Elon's directive for the Merlin engine was simple: build something as straightforward and inexpensive as possible. So what does that actually look like in practice? Inside the main body of a rocket, there are two propellant tanks. One carries oxygen and the other carries fuel. The oxygen side works essentially the same way across all rocket types because combustion requires oxygen, and by feeding a pure and consistent supply directly into the engine, you get a powerful and sustained burn all the way to space. To turn oxygen into usable rocket propellant, you first have to liquefy it. This means cooling it down to cryogenic temperatures, converting it from a gas into a liquid state. The boiling point of oxygen is negative 183 degrees Celsius, or negative 297 degrees Fahrenheit. At any temperature below that threshold, it remains stable as a liquid. The reason for doing this comes down to density. Liquid is significantly heavier than gas, meaning you can pack considerably more potential energy into the same volume inside your rocket. On the fuel side, the Merlin engine burns a chemical called RP1, which is essentially highly refined kerosene. It is cheap, widely available, and already in liquid form at room temperature. SpaceX does cool their RP1 down to just below freezing to gain some of that same density advantage and extract a little more performance from the fuel tanks. When the engine startup sequence initiates, two pumps push both the oxygen and the fuel at very high pressure into the combustion chamber, where the two liquids are combined and ignited. That combustion releases an enormous amount of energy as the propellants burn and expand, building pressure inside the engine. All of that energy exits the combustion chamber through a narrow opening called the throat. The high-pressure, high-temperature exhaust then flows through the nozzle, expanding outward from the diameter of the throat to the full diameter of the nozzle opening. This expansion actually accelerates the exhaust to speeds even greater than what it was moving at when it left the throat, because matter naturally flows from regions of high pressure toward regions of lower pressure. The larger the expansion ratio between the throat and the end of the nozzle, the greater that acceleration becomes. This entire process converts pressure into thrust. The faster you can push that exhaust gas out of the back of the nozzle, the faster the rocket moves in the opposite direction. Every action produces an equal and opposite reaction. That covers the simple version. But we can go a layer deeper and look at exactly how the fuel gets delivered to the combustion chamber, because that tells us precisely what category of rocket engine we are dealing with. In the Merlin design, the twin pumps for fuel and oxygen are driven by something called a gas generator. Think of it as a miniature rocket engine with its own small combustion chamber and nozzle that receives a modest feed of oxygen and fuel from the main pump. Except instead of producing thrust, this mini engine fires its exhaust directly into a set of turbine blades. The pressure from that combustion spins the turbine, which connects to a drive shaft, linking the gas generator back to the main fuel and oxygen pumps. Everything rotates together as one system. After the gas generator exhaust has done its job, spinning the turbine, whatever remains gets vented out through an exhaust pipe on the side of the engine. This is what engineers call an open-cycle gas generator, and it is a design concept that traces all the way back to 1944 and the very first long-range ballistic missile ever built, the German V-2 rocket. So when Elon asked for the simplest and most affordable engine possible, this is exactly what his team delivered, which also means there was significant room to improve upon it. So what happens when you close that gas generator cycle and keep all of that exhaust pressure contained within the engine? We are about to find out. The Merlin engine continues to serve SpaceX exceptionally well to this day and will likely keep doing so for several more years. But when the time came to begin development on the next generation of SpaceX vehicle, an entirely new generation of engine would be required to match it. With Starship, Elon Musk handed his engineers a new mandate: build the most complex rocket engine ever created, give it the highest thrust-to-weight ratio of any engine in existence, and power it with a propellant that no rocket program has ever used before. The era of falling back on 20th century designs was over. This was the moment to completely reinvent the rocket engine from first principles. It starts with the fuel. Rather than kerosene, the Raptor burns methane. Just like oxygen, methane must be liquefied at cryogenic temperatures before it can serve as viable rocket propellant, which adds an additional layer of complexity to the overall system. But the trade-off is absolutely worth it. Kerosene is a long-chain hydrocarbon, which means it is extremely difficult to fully combust and convert entirely into gas during the burn. You inevitably end up with solid residue left behind as a byproduct, even within the intense environment of a rocket combustion chamber. That leftover carbon material is what we would generally call soot, the same black residue you would find coating the inside of a chimney. And like a chimney, it tends to cling to the interior surfaces of the engine and accumulate over time in a process called coking. For a conventional rocket engine that drops into the ocean after a single use, this is a non-issue. But in a reusable engine like the Merlin, all of that carbon buildup has to be scrubbed out between every single launch. And that cleaning process is simply not compatible with the rapid reuse schedule Elon envisions for Starship. The goal is multiple launches per day. Methane, by contrast, is mostly hydrogen with just one carbon atom for every 4 hydrogen atoms, making it far easier to combust completely and leave virtually no residue behind. If you have natural gas in your home, it is almost entirely methane, and you can run it through your furnace or stove all day long without worrying about carbon accumulation. That is the fuel. Now, how does the internal architecture of a Raptor compare to the Merlin it succeeded? The Raptor operates on what engineers call a full flow staged combustion cycle, and it is an extraordinarily intricate arrangement of pumps, turbines, and interconnected plumbing. Let us go back to the engine. In the Raptor cycle, the liquid propellants travel from the tanks to the main pumps and then directly into a pair of separate gas generators. Both the fuel and the oxygen feed into their own individual turbines. Rather than everything spinning on a single shared shaft, there are now independent turbines and pumps dedicated to each propellant, all integrated into a unified assembly known as the turbopump. Starting with the oxygen side of the Raptor, cold liquid oxygen flows down from the tank into the pump, which feeds it into a preburner. That is the miniature combustion device mentioned earlier. Because the gas generator and the pump are now integrated into the same unit, nearly all of the liquid oxygen passes through the preburner, where it combines with a small quantity of methane and ignites. This converts the liquid back into a gaseous state, and because matter moves from higher density to lower density, the oxygen accelerates rapidly into the generator turbine. That turbine connects via a short drive shaft to the turbopump, which draws the liquid down from the main tank above. Because only a small amount of methane is introduced into the preburner, the oxygen is not being consumed or wasted. It is simply being heated. By vaporizing the liquid, the volume increases dramatically, which dramatically increases the pressure within the system. This is the fundamental source of the Raptor's extraordinary power. That superheated oxygen gas is then pushed through a series of injectors down into the main combustion chamber. But before we move on to the methane side, there is a significant problem with what was just described. If the gas generator turbine drives the pump, and the pump feeds liquid into the gas generator, how does the whole sequence get started in the first place? A conventional rocket like the Merlin-equipped Falcon 9 carries an onboard helium tank for exactly this purpose. During the startup sequence, helium is released into the gas generator, which spins the turbine and sets the entire cycle in motion. For the Raptor, SpaceX uses specialized equipment built into the launch mount to externally spin-start the turbines from the outside. This is precisely why the Starship launch structure is referred to as Stage 0 for the main rocket. It is an essential and active participant in the successful ignition of the booster. Now over to the methane turbopump. This sits offset on the side of the engine, running in parallel to the oxygen pump. Cold liquid methane flows in through the top of the unit, but instead of heading straight to the preburner, it takes a detour. Fresh out of the fuel pump, the cold liquid is redirected through a pipe and routed down toward the engine nozzle. This is how the Raptor avoids melting itself. Liquid methane flows through channels built into the walls of the nozzle and combustion chamber, drawing heat away from the metal through conduction. As the liquid warms up, it moves away from the combustion chamber and back toward the methanes and turbopump assembly. The now heated liquid fuel enters the preburner from below, where it first meets a small supply of cold liquid oxygen and ignites. Just as before, the rapid expansion from liquid to gas drives a turbine connected by a drive shaft to the fuel pump above. The turbine also propels the now gaseous methanes sideways back toward the main body of the engine, where methane injectors and oxygen injectors finally converge, and the two hot gases meet inside the combustion chamber. This gas-on-gas reaction takes place at pressures exceeding 300 times the ambient atmospheric pressure at Earth's surface. The latest builds of the Raptor 3 engine have approached nearly 400 times ambient pressure during testing. And because matter always flows from high pressure toward low pressure, the turbopumps themselves must operate at an even higher internal pressure of around 600 times ambient. If they did not, combustion gases would flow back up through the engine into the propellant tanks, and the entire vehicle would be destroyed instantly. The only way to maintain those extreme pressure levels is to eliminate the exhaust pipe from the gas generator entirely. That is why the Raptor is called a closed cycle, as opposed to the Merlin's open cycle. In a Raptor, all of the pressure generated by both preburners stays sealed inside the system. This is another area where methane's cleanliness as a fuel becomes critical, because without an exhaust vent, any soot produced would accumulate inside the engine almost immediately and destroy it. If you attempted this same closed cycle design using kerosene, carbon buildup would ruin the engine within moments. This containment of all propellant flow through the preburners and into the combustion chamber is also where the term full flow originates. Every drop of fuel and every molecule of oxygen passes through the gas generator before reaching the main chamber. And the staged combustion part of the name refers to the fact that ignition happens twice. First in the preburner, then again in the main combustion chamber. If all of that sounded enormously complicated, that is because it genuinely is. Elon himself has described the ignition sequence of a Raptor as a delicate dance between the fuel system and the oxygen system. Everything is interconnected and everything influences everything else. If anything goes wrong, or even if the methane and oxygen cycles fall even slightly out of step with one another, the engine detonates. So we understand how the Raptor does what it does. Now let us look at what that actually means in terms of raw performance. The Raptor is a relatively compact engine that produces a disproportionately massive amount of thrust. The current Raptor version 3 generates 280 metric tons of thrust at sea level. That is not the highest thrust figure ever achieved by a rocket engine. That record belongs to the F1 engine that launched the Saturn V moon rocket, which produced more than double the thrust of a single Raptor. But the F1 was also an absolutely enormous piece of machinery, large enough to park a Jeep inside. By comparison, the Raptor is remarkably compact at 3 meters tall and 1.5 meters wide at the nozzle exit. That compactness allows SpaceX to install 33 of them into the 9-meter diameter base of the Super Heavy booster. The closest comparable engine in terms of roll would be the RS-25 that powered the space shuttle and has since been adapted for the SLS lunar rocket. But the RS-25 only produces around 190 metric tons of thrust while being roughly twice the physical size of a Raptor. This gives SpaceX a thrust-to-weight advantage that no other engine currently matches. The Raptor achieves this by running its combustion chamber at a higher pressure than any other rocket engine on the planet. Raptor 3 operates at a chamber pressure of 350 bar, which translates to over 5,000 pounds per square inch. For context, the Merlin engine operates at around 100 bar. And since the throat and nozzle convert pressure into thrust, more pressure means more thrust output. That is the essence of what makes the Raptor what it is. By any reasonable measure, it is an extraordinary and borderline extreme piece of engineering. It operates at pressures that would crush a submarine hull. It is perpetually one misstep away from destroying itself. And SpaceX needs 33 of them firing in perfect unison just to lift a single Starship off the ground. But none of that is a flaw in the design. It is the entire point. Because reaching Mars and establishing something permanent there does not happen with a simple engine. It requires this one. The long-term vision for Starship places it among the most consequential vehicles ever built by human hands, right alongside the first sailing ships that crossed the open ocean and connected the continents of the world. Starship has the potential to connect the planets of the solar system. But before any of that can happen, we first have to learn how to fully harness the Raptor.